Hi, my name is Richard. I'm a second-year PhD student working with Joey and Jan. I'll be talking about Tune, which is a distributed hyperparameter search library built on top of Array. So recall this slide from Robert's earlier presentation in the morning, which is effectively like the Array stack. And Tune sits right in this corner. It's an application built on top of Array, utilizing Array's task and actor APIs to effectively and seamlessly distribute your hyperparameter search. So before we dive into the details of Tune, let's take a step back and explain what exactly are hyperparameters. So here on the screen, we have an example, convolutional neural network. Convolutional neural networks are a type of neural network that are very powerful and are attributed to many of the recent advances in computer vision. However, one thing that gets less attention is the amount of time and effort spent on designing and training these networks. Changing the shape of the neural network, each size of each layer, the number of layers, the parameters that dictate the learning dynamics, such as learning rate, all of these things can make a huge difference in performance. And all of these knobs are what we call hyperparameters. Now, you might be wondering, well, okay, these are just simple numbers. They don't actually matter that much. Well, I'm going to convince you real quickly that they actually really depend, the performance of your algorithm really depends on the hyperparameters that you set. So for example, here's a recent study of of changing the size of the neural network used in a very popular deep reinforcement learning benchmark. And you can see that the blue line represents using a 64 by 64 hidden neural network. But if you increase the number of the size of some of these layers, you can actually completely diverge the performance. So the point here is that the hyperparameters really dictate the performance of your model. And so now we understand that hyperparameters are important, but why do we need a framework for doing the search over the hyperparameter space? Well, without an automatic framework such as Tune, you'll have to make manual adjustments to the hyperparameters over the course of many training runs to arrive at whatever you consider your optimal values. Hyperparameter tuning algorithms make the process of determining the best hyperparameter settings easier and less tedious. Also, compute resources are expensive, and model training is becoming more and more computationally intensive. Since 2012, there was a recent study by OpenAI shows that the amount of compute used in the largest AI training runs have increased exponentially over the last 7 years with a 3.5-month doubling time. So that basically tells you that we have these expensive resources and we need to use all of them, and we should be very smart and intelligent about how we use them. And finally, the time to train a model to a state-of-the-art performance can take order of days and if not weeks to finish. So reasonably, we want a system that can maximize our model performance, effectively utilize our resources, and do this with minimal time and price. So let's talk about Tune now. Tune is one of the only hyperparameter tuning frameworks that is built with deep learning as a priority. So this means that Tune has the ability to multiplex training on multiple GPUs across multiple nodes. So for example, using Ray as a backend, you can do highly efficient training in certain situations, such as sharing one GPU across 4 different models if the models aren't particularly large. And if you have a cluster of, say, 20 GPUs on 20 different machines, you can train up, say, 80 models just using these resources. Now, talking about a cluster, Tune provides seamless distributed execution. So Tune works on your single machine, parallelizing the search across cores, and this is what you'll be doing in the tutorial. But also, you're given the ability to scale from a single machine to a cluster without changing a single line of your code. Tune also offers many algorithms to help guide your search. But if you're not satisfied with the offering, Tune offers a very simple API to add new model search algorithms. And best of all, Tune is compatible with any deep learning and machine learning framework. So that's a little bit about Tune's features. Now, Tune is very easy to use. Unlike many hyperparameter search libraries, you don't actually have to restructure your entire code base around it. You can use one of two interfaces, so either a function-based API for quick prototyping, or a class-based API, which enables more advanced features such as training checkpointing. And in my experience, modifying a code base to use Tune typically takes less than 10 lines of code. The tutorial later will be based off of the MNIST examples that I take straight off the Keras examples page. So it's really not too complicated to do. Now, we can also talk about what Tune offers specifically for hyperparameter optimization. So underneath the Tune API, Tune offers one thing, which are search algorithms. These are in blue. And these are basically algorithm-based techniques for hyperparameter optimization. And these are typically what you would find in if you search in GitHub for hyperparameter optimization, and include things such as hyperopt, sigopt, and random search within this space of techniques. Now, there are a few algorithms that are implemented, but most algorithms or services can be adapted to a search algorithm in Tune in just a few lines of code. In yellow, Tune offers trial schedulers, which are execution-based as opposed to algorithm-based techniques. So these techniques allow Tune to be very resource efficient. For example, Hyperband, which is a algorithm from the RISE lab, or the AMP lab previously, is a very efficient resource-based algorithm that kills the lowest performing trials, ensuring that you're maximizing the utility of your cluster. Now, Ray's Actor API is a great fit for these algorithms because it enables, actors enable features such as early termination and modifications to the model while the model is training. Now I've talked about trial schedulers and search algorithms, but one thing that will be really hard to find without using Tune is the ability to combine these two things within a single search run. So recent research has actually shown that certain combinations of search algorithms and these execution-based techniques can actually accelerate your search process. And Tune provides that with just 2 lines of code. So we'll quickly highlight some of the nice features of Tune in code, and most of these things will be covered in the upcoming tutorial, but let's walk through them together right now. So this example will use the function-based API, as mentioned earlier, for quick prototyping. And if you want to look for more complex examples, you can look at the GitHub. So Tune is included as part of Ray, and it actually runs on other execution engines, but let's use Ray for this example. So we'll start by importing Ray and Tune and then initializing Ray. So we have here a regular Python function for training your model. And it loops over a data set and calculates some accuracy as it goes over the data set. Now, in order to make this Tune compatible, we can make 2 minor modifications. The first on the top is we modify the function signature with a reporter argument, which is a Tune-specific object. And then we use this reporter to monitor intermediate results and early stop bad evaluations of trials by reporting metrics within the training loop. So we'll then call run experiments on this function within some sort of format. We'll walk over this in the tutorial. And Tune will then execute a training run of this function. You can also specify a stopping criteria, being mean accuracy as 99, and also a search space. And this is a very simple example. There's more complicated search spaces that Tune supports, and you can find them in documentation. So these evaluations will be executed in parallel, either on your local machine or on your cluster. And one nice thing is that while you're doing the search, using the reporter, Tune will automatically take care of all the logging of your results and outputting the visualization into TensorBoard. So the TensorBoard exercise we used earlier for the RLib demo or tutorial actually uses Tune underneath the hood. So for more complicated use cases, such as using a larger cluster, you can specify your resource requirements with the trial resources argument. And one nice thing since the last RISE camp is now these actually can be fractional values, so you can support multiple training runs on a single resource. You can also continually sync your results with S3 with another argument as the upload directory. And you specify things such as max failures for fault tolerance purposes. And you can also specify your favorite scheduler or search algorithm for hyperparameter search with yet another argument. So there's really not that much to tune in terms of user API. And I suspect that after you use the tutorial, after you go through the tutorial, tune should be really easy for you to use within your own use case. So final bit, tune as part of Ray is rapidly growing. So as you can see, and if you haven't already, you can check out Ray, tune on the Ray documentation. And so we can start the tutorial. You'll have to go to risecamp.tech. And make sure that, so make sure that you go to the notebooks rather than using lab for some JavaScript purposes. And after you finish the tutorial, there's a survey at the very bottom of the tutorial page, and be sure to fill that out. And I'll be around for questions. Thanks.